This video is looking at doing t-tests for a hypothesis test about the mean. So remember, we use t-tests, or we use t-values, when we're looking at a situation where we've got a sample and we know the sample standard deviation, but we don't know the population standard deviation. Our steps for this are going to be the same as our formal hypothesis test. So identify our claim, write it symbolically, state the null and alternate hypotheses, decide on our alpha, calculate our test statistic and critical value. Note that we are looking at the formal test for these. Because of the limitations of our table, we do these with the formal test, but if you're using Excel, you can calculate p-values and do these using the p-value method as well. Step 5, reject the null hypothesis if our test statistic is in the critical region. Right, again, this is our decision step. If you choose to do this with the p-value method, it's still going to be rejected if the p-value is less than alpha. And 6, write a statement addressing the claim or the question. So same as before. The only difference is, because we don't know the population standard deviation in many cases, we end up using the t-test instead of the z-test. And that's to account, remember, for the higher degree of uncertainty that we have when we've got a small sample and we are not able to approximate the population standard deviation. So the degrees of freedom for testing a mean are the same as they were for doing an estimate, n-1. But what's different is we now have the situation where we sometimes have one-tailed tests and sometimes have two-tailed tests. So that table, and I'm just going to quickly put the table on the screen, uses the fact, right, and has two scenarios, one-tailed test and two-tailed test. So make sure you're looking up in the correct column for the scenario you've got. Also, make sure that if you have a left-tailed test, this is always giving positive values. The left-tailed test has to be same value but negative. So let's look at an example. The technologist claims that the average time to drill an oil well is 23 days. His coworkers suspect this is too low. They check the records, and for that sample, the time to drill was 24.7 days with a standard deviation of 3.9. Is there sufficient evidence that the average is over 23 days? And then we're asked to do two different things. Test at the 1% significance level, and secondly, test at the 10% significance level. So again, focus on that question to figure out the claim. So the average is over 23 days. So over is greater than. We're looking at an alternate hypothesis. So direct opposite is less than or equal to, but remember we're testing against the equality, so we can write this as equals 23 days. Always focus on the alternate hypothesis to decide if this is left, right, or two-tailed. So in this case it's right-tailed, because we see the greater than pointing to the right. Our other pieces of information, we have our n is 22. Our standard deviation is 3.9. Our sample average is 24.7. And for the A question, we're testing at the 1% significance level. So alpha is 1%. So because we know S and not sigma, sample standard deviation and not population, we're going to use our T calculation. Take a moment and do the calculation. Pause the video if you need to. So T works out to 2.045 for our test statistic. If we're looking at our critical region, 0.01, so that's right-tailed test, it's our area in one tail. Degrees of freedom, 22 minus 1 gives us 21. So if we go over to our table, we want one tails 0.01, so this column right here, and we're going to go down to 21, So just scroll down a little bit, and we see our z-score there. Sorry, not our z-score, our t-score of 2.518. So if we put that on our chart, remember the critical value that we got out of our table is the one that separates our critical region from our test statistic. So that's right along here. 2.518. So our 2.045, not further this way, it's a little bit to this side. So there's our test statistic. So we can see it's not in the critical region, and remember the nots go together. So not in the critical region, do not reject H0. So we're not rejecting this one, it means we're not supporting this one. So our final conclusion should say there's not enough evidence to support the claim that the average is over 23 days at the 1% significance level. Now, this is not to say there's no evidence, but there's not enough evidence. Certainly 24.7 is higher than 23, so there's some evidence, but not enough at the 1% level. So the second part of the question says, we'll test it if you test it at the 10% level. So most of this question is still the same, right? Our claim is still the same, it's still right-tailed. Our test statistic is still going to be the same calculation. What's going to change, though, is our diagram. So let's put another diagram in here. And I have one, but it's not visible. So give me a sec here. Drag it to where it'll be visible. So if we look at that, we can see that what changes is this is at the 10% level. So if we look on our chart, instead of looking at the 1% level, we're looking at the 10% level down at 21. Our critical value is 1.323. So if we compare that same critical value of 2.45 now, it's going to be way over here. So this time our critical value is in the critical region. So we're going to come up to the other conclusion. We're going to say of those two, H0 and H1, that we're rejecting H0. I'm actually just going to repeat those two down here for this question, right? So our H0 is that it's equal to 23 days, and our H1 is that it's greater than. Also notice when I'm writing these, I'm not saying H0 equals 23 days, I'm saying the mean equals 23 days. That's kind of important. What is our hypothesis about? It's about the mean. So this time we are rejecting this, so we're supporting this. But that's not the conclusion we came to in A. This sort of thing is part of why some people think, oh, you can't trust statistics because you can manipulate them to how you want. And they think these two things are saying the opposite. But they're not actually. If you read the actual statements, it's saying there's enough evidence at the 10% significance level. In other words, we can be 90% sure that this is the case, that it is more than 23 days. But there's not enough evidence at the 1% significance level, says we can't be 99% sure. So if you want to be really, really certain, this isn't enough evidence. But if you're like 90% is good enough, there is enough evidence. So for the situation, that significance level can make a difference as to what your conclusion is. But saying there's not enough evidence is not the opposite of saying that you do support the claim. So be careful right? The not enough is saying we need more evidence. It's not saying the opposite. So that's pretty much the t-tests in a nutshell. It's really very much the same as the z-test, just that we're using the t-calculation and the t-table instead.